talk about how to encode booleans, which is neat, but probably haven't convinced you yet that we can like encode any kind of computation we want. Like Boolean, just being able to do booleans is a far cry from doing it. So I don't know if we'll get all the way there today, but we'll keep going. So just to remind you, right, our idea for encoding booleans was normally we think of having a boolean. If you want to do something with it, you pattern match on it. Say, is it true or is it false, and I'm going to do something. But in lambda calculus, we only have functions, so we kind of flip it around and say, a boolean isn't something that we can look at to see which it is. A boolean is something we can apply as a function, and we can apply it to some things, and it'll choose between one of them, which is just as good. And we got there right by doing the fold and stuff. So, like on the module, it asks you to encode some other data types. And a really great way to start, right, is to start by writing out the type of the fold for that thing in Haskell, and kind of think about how we, moved the thing to the front, and it says, okay, it turns this thing into a function of this type. And you want to think about representing it using lambda calculus terms that represent those kind of functions. So let's just false is lambda t dot lambda f dot f. True is lambda t dot lambda f dot t. And I just want to show you, by the way, a couple of things about this. Okay, there's quit, of course, help. So you can load and save definitions, and then you can show the current definition. So if I say show, it shows me the things that I have defined currently, and then you can load them and save them. So that's going to be helpful on your homework, so you don't have to so I could just say save. So like Google Docs, and if I quit, right, Google.lc, it just has those definitions in it. That's all. It's just a text file. So this is how you can play with definitions, and then you can save them, and then you can turn that in as part of your module. But you can also obviously save your work in between, so you can restart this. And we got those definitions. And I think we had last time done not, right? So we figured out, I don't remember how not worked. There were actually a couple ways we could do it. But so not takes a boolean, and then what did we do to return the negation of that boolean?
One of them was listing false first, right? Or what's that? And then you list false first, and then it chooses false as if it were true.
Right, that's right.
False is true.
Yeah. So if B is true, I want to pick false and vice versa. So how would I write that? So how do I, in the lambda calculus, how do I use a boolean? That? Yeah, we can do it that way too. So one way to think about this is, all right, I took a boolean as input. I need to return a boolean as output. And what is a boolean? Well, a boolean is a function that takes lambda t, lambda f, and then returns one of those two things. So I could think that way and say, all right, well, then I want to return lambda t, lambda f. And now here I've put something that chooses between t or f. But I want to choose based on B. So how do I use B to choose which of those I want to return? Too early? This is the key idea. The way we're representing booleans is as functions. So the only way I could use anything in lambda calculus is by applying it to some arguments. Yeah. So whenever in the lambda calculus, if you ask, how can I use blank? I want to use blank. The answer is always, you apply it to some arguments. That's the only thing you can do. You just have functions, right? So if I want to use b, if I want to use b to decide on something, I do that by applying b to some arguments. And so what arguments do I want? So,
You want to flip those?
yeah, I want to flip them, right? Because if b is true, I don't want to return t. Because then that would make this whole thing represent the function that takes t and f and returns t, which that's true. So I want to, yeah. Now, of course, one thing to remind you of, right? The fact that they're named t and f doesn't matter. The important thing is which one is first and which one is second. So don't name, if you name them lambda f, lambda t, you're just going to get yourself really confused. But, cool. So we can define it that way, right? We could also say it takes a b. Well, it's not 2. And we can just immediately say, well, the thing I want to do is use b to choose between false and true. So I could just say b, false, true. They're a little different the way they're defined, but they end up doing the same thing, ultimately. Okay. But in both cases, the important point is to use the Boolean b, I apply it to some arguments. It's just like writing an if. Right? Just imagine that I wrote if b, then false, else true. Right? But it's in this language I get to leave out all the keywords if, then, and else, which is kind of weird. But okay. Let's do and. So let's do this one together up here, and then you all can get little groups and see if you can figure out how to do 4. All right. So I'll tell you, kind of walking through my thought process for doing and. Okay, so and is a function that takes 2 booleans as input. So I can immediately just say, all right, we'll call it I'll call them p and q, lambda p, lambda q. Okay, so I got my 2 booleans, and now I need to return a boolean, which is the and of p and q. And I can't pattern match on p and q, right? But I can, I can use them to decide between 2 things. So I just think, well, let's see. How about if I use p to decide something? Like if I wrote an and as with a bunch of if statements, how would I do it? I'd say like if p, then what? Well, if p, so I could, say, okay, let's just try thinking about this. What if I had an if p? What would I put in the blanks? Well, if p is false, then I definitely want to return false, because and of false and anything is false, right? So I could go ahead and fill in false here. What if p is true? What do I want to do then? Or what do I want to return?
You want to check q.
I could check q. Okay, so I could say,
Like parentheses of q.
yeah. Okay, so now if q is true, what would I return?
True.
True. And if q is false, what should I return? That's false. False, okay.
Does that work?
Does this work? Now let's try it. The way I can try it is I can say and, true, true. And remember, if I just say this, because this is going to give me a Boolean, which is a function, it'll give me some lambda, then there might be some stuff inside it that's not reduced. And so the way I can force it to fully reduce is just by applying it to some arbitrary arguments that I'm gonna call t and f. And so ultimately, right. The point is, this is a function that chooses between 2 things. It's a Boolean. So I'm going to give it 2 things to choose between, so I can see which one it actually chooses. That way it'll fully reduce everything. This should give me t. Yes. Okay. And true, false. Yeah. Is false. False, true, false. False, false, false. Okay, that works. Cool. Can anyone think of a way to simplify this at all? Is there a different way you could do it that would be shorter? actually a nice principle that you can use to simplify things in any language, not just the language calculus. So this says, what is it? This means if Q, then true, else false. How can I simplify that? It is too big.
It's kind of saying if you could, it's basically like, the way I'm thinking about it is Q being true, otherwise it's false,
Right?
but not quite sure how it would,
Yeah, I mean,
like, cause if Q is, you don't necessarily have to check it. It wouldn't be like a check, it would be like just saying Q is true, otherwise it's false.
yeah, I mean, I think you're on the right track, but, right, so, in what situation would I return true here? Yeah, so forget about P, but just looking at the Q true false. So when do I return true? When what? When Q is true, right. And when do I return false? When Q is false. So why not just return Q? Q is already true or false. I don't need to say, if this thing is true, then return true, else if it's false, return false. I mean, think about if I said, if this is equal to 3, then return 3. Else if it's equal to 5, return 5. It's like, no, just return the thing. Like, you don't need to check. It's a Boolean, right? It already is a Boolean. So this is not just about lambda calculus, right? If you write this in any language, Python, Java, it doesn't matter. If you say if some condition, then return true and else return false, you never need to say that. Anytime you say if something return true and else return false, just delete the if and just return that Boolean, because it's already a true or false. That's what you want. So I can just say P, Q, false. Right, so it's basically saying, look, if P is true, then we're going to just return whatever Q is. And that's going to be the output of the whole thing. But if P is false, then the answer is false. We don't need to look at Q. That's probably the shortest way to write it. There's other ways you can write it, but let's do it. All right. So take a few minutes. Do just like the three of you. I know you're like spread out, so you're gonna have to move. But three of you and three of you. Just get together and see if you can figure out how to write 4.
P is true, it's going to be true, and then if Q. Kind of start that. Yes, because true run was first. Yeah.
then, you know, we can start to, no, I can't say that. Why can I not say this?
Because it's the opposite, you want to do or, and then.
Yeah, or I have to,
Takes two.
yeah, I can't write like infix.
Yeah.
Or, right, so it's like or, true, false,
So you can write any number of things and then give the two arguments at the end?
yeah, sure.
Okay.
Woo. So, the way we're doing things is not particularly efficient, right? So I said, like, you know, Haskell, for example, is based on the lambda calculus. Haskell doesn't actually encode all its data types in lambda calculus like this. Like, it actually has built-in data types you can pattern match on, which is way more efficient. But theoretically, you could do this, right? Also, there's also way more efficient ways to even reduce the lambda calculus. I mean, we're just doing it kind of this naive, well, you just like substitute this whole thing. Like, imagine you have a lambda term, this is like lambda x, and then it uses x 5 times, and then you apply it to some big argument. The way we're doing it, you just literally take that big argument and you just like copy it 5 times, and you just like, the size of your term kind of blows up. Haskell does not do it that way, right? It just like kind of saves a pointer to that thing, and then all 5 places where x occur like share a pointer to that thing, and so when it gets evaluated, they all can see that. But whatever, we're just yeah.
Another question. Charlie, can you
Scroll up to
yeah, like where you wrote the example. Could you do like and or 1, 2, like instead of using true false for everything? Or
we don't have anything named. We don't have anything that named 1 or 2 defined yet. So.
oh, so you have true and false.
Yeah, we define true. Like we literally have nothing except lambdas, and we're just defining some things. But like there's no numbers built in. No, we're going to talk about numbers next. We have to make our own numbers. I mean, literally, and it's like all you have is functions.
Okay.
It's functions. Turtles all the way down. All right. Any other questions about this? I'm confident that you all could now like do XOR, implied, whatever. It would all be kind of the same. You just take some booleans and you just kind of think about how to do that. But this, you know, and or not is enough, and true false. But is that all we need? You could also, I guess, you can define or as like using De Morgan's law or something like not of not P and not Q or something. But that would be even less tight for a second. I know. All right, let's think about numbers. So, let's see. Let's recall. Sorry, I can't see this. So I guess maybe I'm kind of doing some of your homework for you, but it's okay. This is the simplest and stupidest, but most elegant way to encode natural numbers, right? So I have Z, that represents 0, and then S stands for successor, that means adding 1, right? So ZS is a nat, that represents 1. Sorry, not ZS, SZ. SZ represents 1, and then I could have S of SZ, that represents 2, I could have S of SZ, and so on, okay? This is how we're going to represent natural numbers. And then, what would be a fold? And I'm going to write it with the arguments in the other order. Just so like the nat is going to come first. And then we're going to take, you know, like a B for the Z case. We're going to take a B to B for the S case. And we're going to return a B. And in fact, and then I could put parentheses here if I want, just to emphasize think about this is turning a gnat into a function. Okay. I'm actually not even going to go ahead and implement this because it doesn't matter. The point is, right, this tells us that functions that look like this are how we can represent natural numbers in lambda calculus. Okay. So a function, a number in the lambda calculus will be a function that takes two arguments, just like a Boolean, except instead of just like choosing one of them and returning it, basically it's going to take the first argument representing 0 and the second argument representing successor, and it's going to apply this argument to this some number of times and return the result. So like if it ignores this argument and just returns this, that represents 0. If it takes this function and applies it to this thing once and returns that, that's representing 1. So basically the number is represented by how many times it applies that function to the other argument. Okay. Said another way, right? We thought of Booleans as a little machine that lets you choose between two things. Now we're thinking of a number. A number, like what is a number? What can you do with a number? You can repeat something that many times. That's what ability a number gives you. So, right, think of it as a machine that you give it a starting thing and kind of another little machine, and then just like run that thing through the machine that many times. So this turns that into a function which repeats something in that n. Okay. So that's oops. So 0 is, I'll call it lambda z, lambda s. You know what? Actually, I don't know. For whatever reason, people always put the arguments in another order. Like whenever I've seen natural numbers talked about in the calculus, people always put the s first and then the z. Which, you know, maybe we should have listed them like this, so the order corresponds. But okay, so we'll do that. An s and a z, and 0 means it's going to ignore the s and just return the z. So it's actually the same as false, interestingly, but we're kind of thinking of it in a different way. But literally it is the same function as false. So we could have just defined 0 equals false, which is kind of odd. I mean, we usually actually do think of 0 and false corresponding, but in the lambda calculus they're literally the same thing. Or at least this way of representing numbers and arguments. Right? What is 1? 1 is lambda s dot lambda z dot sc. Right? It takes that function s and the argument z, and it applies s to z one time. That represents 1. 2 is going to be lambda s lambda z s z, and so on, right? Maybe let's just write successor together. So successor I want to be a function that takes a number and returns the number that is 1 greater. Okay, so again, my thought process is, okay, this needs to take a number, so I can go ahead and write a lambda. I'm going to call it n, because it's a number. I don't know what's going to go here yet, but at least I can write this much, because I know it's a function taking a number. Okay, now I need to return a number. So you could, one way you could do it is you could go ahead and write lambda s, lambda z something, because you know it's going to be a number. We could also just say, all right, well, what number do I want to get? How do I get it? Wait, maybe we have to do that. Yeah, okay, no, we do. Yeah, so this is the way I think about it. I'm taking a number. Now I need to return a number. So yeah, what is a number? A number is a function that takes an s and a z and does something. So I can just go, I'm going to put parentheses to emphasize that like we're thinking of it as taking a number and returning a number, but I don't actually need the parentheses, right? They're redundant. So lambda s, lambda z, and And now I need to apply S to Z some number of times. How many times do I want to apply it? N plus 1. So the way I can use N, right? I mean, I can't like check and see what number it is, but I can use it to repeat something N times. So in particular, if I say N S Z, that says repeat the function S on Z N times. Okay, that's not quite what I want. I want S on Z N plus 1 times. Okay, so I could just add one more S outside this like this. Right? Or I could also put the S on the Z here. I could just say like start with SZ and then apply S N times. Either one would give me N plus 1. Any questions about this? Does it make sense, kind of? Silas?
So adding the S somewhere just adds one.
Well, it's not like we could just add the S anywhere. I
Well,
mean,
yeah, but like if you could add it before the Z again.
yeah, I could either do this, or I could like this corresponds to saying, yeah, let's repeat S on Z N times, and then call S one more time on that. Or I could say, actually, I want you to start with SZ, and then apply S to that N times, and that would also give me the same thing, right? It's just like, where does the extra S go? I kind of like doing it this way. I don't know why. It just seems like, see, okay, first let's kind of recursively do N times, and then the last thing I'm going to do is like do one more. Somehow that feels more normal to me. So I encourage you when you're doing this, right, try to, you can even like write out notes as you go, or whatever, it helps, but try to think through it step by step like I'm doing. Don't try to think in terms of like reducing it and figuring out what's actually going to happen, because like no one can do this in their head, right? The thing that sucks about this is that sucks. Okay. The thing that sucks about this is that there's no types, and so if you like screw up and for example, if I wrote if I put the S here, that doesn't really make sense, because like S is a function that we're applying to Z. We can't apply S to itself. I mean, but the thing is we can't. Like lambda calculus has no problem with this. It's just going to give us some random lambda term that doesn't really mean anything to do with a number. It'll just be something. But like that's the thing, it can't tell us, it has no idea what we intended or what these things are supposed to represent. They're all just lambdas. And so there's no kind of error messages, right? Literally, you could have a parse error. That's the only kind of error you can have. And so debugging this is actually, it can be pretty tricky. You can try some small examples. You can, try to think through it step by step. You can ask me for help. Send me your definition on Teams or whatever, and be like, this isn't doing what I think, but, what's going on? So, let's try this out. So if I say successor of 2, and then I can apply that to some constants S and Z, and I got SZ, right, S3, that works. I think we can kind of see what's going on here. So what happens here? So this is the thing we said is succ, so it expanded that definition. And then the first argument we supplied was 2, and so that goes to the end, right? So notice how here it reduced that and it substituted in the 2 for n. So now we have 2 SD, right? And then it substituted in the big S and the big Z. So now I just have, right, according to the definition of succ, I have 2 SZ and then an S applied to that one more time. And then, well, what's the definition of 2? It's this. And so then it did that with S and Z, and then we got that one more S. So I could even, I could define 3 as succ 2, 4 is succ 3, 5 is succ 4. And I can say, okay, there's 5, 1, 2, 3, 4, 5. Yep, that's 5. So on the module, you will get to write addition and multiplication in numbers, which is not necessarily as hard as it sounds. Like the code for it is actually very short. It'll take a little bit of thought, but think about what numbers mean, what you can do with a number, right? A number lets you repeat something that many times. So think about, all right, well, if I want to add, what is it that I'm repeating? Like, what can I repeat on what to get a result? Okay. Cool. All right. I think what I want to do in the last few minutes. Well, okay, here's what you can do. I'll just give you a little puzzle and we'll think about it, and then we'll talk more about it next time. So, I'll give you another mystery function. So, can we implement a function of this type? What do you think? Do you have any ideas how we might implement this? And it is actually possible. Let me fill in that. Right. So I got my argument f. F is a function from a to a. I need to output an a. So where could I get an a from?
Just the function.
Yeah, the function is the only place you can get an a from, right? So the only thing I could possibly do is apply f to something. But, well, what do I need to apply f to? I need to apply f to an a. Okay, so where should I get an a? I mean, so I could say, well, I could say f again. And then, well, that, like this. So doing it this way, I'm never going to stop writing f, so that's right. There's something else I could write here, though. There's actually one other place that I could get an a from. Mystery. Oh. So mystery returns an a. So what do I need to put here? F. Okay. Was. So Haskell will accept this. Anyway, whatever. We don't have much time, I'll just say. Haskell accepts this. It's like, it's fine with this definition. Now you might think this definition is completely useless because, like, how would it ever actually, like, it looks like in order to figure out what mystery f outputs, you need to figure out mystery f so that you can give that to f. And you're like, well, but then you need mystery f again, and then you need mystery f again. Like, you never make any progress. Turns out that's not quite true. It depends on what f is, and it depends on what type A is. So the point is that because Haskell is lazy, sometimes f might not need to look at its argument. And if that happens, then you get to stop, and you can say, oh, f can return something without having to look at mystery at all. We're out of time, but very useful. And it's also the key to understanding how we can encode arbitrary stuff in the length calculus. Because we can make something kind of like mystery in the length calculus, and use that to do recursion.